Hello and welcome back to the video series about the Fourier Transform. This is part 2, and as promised, we first start with so-called Fourier Series. And I think the best starting point for that is to talk about trigonometric polynomials. However, as always, before we go into the details, I first want to thank all the nice people who support me on Steady, here on YouTube or via other means. Moreover, you can also download PDF versions and quizzes with the link in the description. Well, then I think for the beginning here, it's good to first recall the idea of a Fourier series. And it's important to remember it always applies to periodic functions. For example, you could imagine that the function looks like that. And if for this example here on the domain we find the interval 0 to 2, we would say that this function is 2 periodic. Obviously, this implies that the function is also 4 periodic or 6 periodic and so on. However, you can also see it's not 1 periodic. Now, for the case that you have never seen a periodic function before, let's write down the definition of this thing. It simply means if you have the input for the function f shifted by the number 2, then the result, the value of the function, does not change at all. So we get out f of x no matter which x we choose. So it's important that this equation holds for all inputs x in R. And now the idea of a Fourier series is that we take a combination of sine and cosine functions to approximate this function here. In which sense we interpret this approximation here, we will see soon, but you can already recognize that the periodic nature of the cosine and sine functions is the important ingredient here. Hence, a sensible thing we could do now is to take the function here and stretch it into the x direction until it's 2 pi periodic. This means we stretch or compress it until this interval here has the length 2 pi. It makes sense because the standard cosine and sine function are also 2 pi periodic. Therefore, we don't change any essential thing, but we make the whole notation simpler. And now what I want to do is to put all these 2 pi periodic functions into a set. And the notation we choose here is that we have the domain R and the codomain R. Indeed, later we will see that without any effort, we can also extend everything with complex valued functions. But for the moment, we can keep everything real. Hence, in the set here, we have functions f that map R into R. And the only property we want now is that they are 2 pi periodic. And as before, this means if we add 2 pi to an input x, we don't change anything. So that's it. It's a well-defined set of functions and obviously not the empty set. In fact, with our linear algebra knowledge, we immediately know that this is a vector space. And because the codomain is chosen as R, we have a real vector space. Please note, this means that you are not able to leave the set by using the addition of function and scaling of functions. If you don't know that, you can watch my abstract linear algebra course. For here, I would say we immediately look at some examples. Indeed, the simplest 2 pi periodic function would be a constant function. So a function that gives the same value no matter which x you put in. If we want, we can say the constant is equal to 5, but obviously this works for every constant. Hence the graph of the function looks like this. And there the periodic property is obviously fulfilled because it doesn't matter which period you choose here. Therefore, also a very nice example of a 2 pi periodic function. Now, after understanding that, you realize you can do whatever you want. The only restriction we have is that we have to repeat it again and again. So if this is the interval 0 to 2 pi, we can do that, and then we repeat it. Then the result looks like that. So definitely a strange graph of a function, but still a 2 pi periodic function. But you could definitely say it's a very complicated periodic function, and therefore we should look at more simple ones. Maybe simple is not the best word, but we definitely have functions we know very well. For example, we have the sine function, which is definitely 2 pi periodic. So in this case, our interval 0 to 2 pi lies here. Hence, this here is just a function that sends x to sine of x. However, another 2 pi periodic function would be x sent to sine of 2x. This is not quite surprising because the periodic property from above is still fulfilled. However, in the picture the function is stretched, so it makes more oscillations in this interval. This means with this number in the sine function, we can increase the number of oscillations in the original interval. And this is the important insight we need for our approximation argument from before. Hence, the choice of the functions we keep simple. We just take functions, sine and cosine functions of this form. And then, also with our linear algebra knowledge, we notice something very important. Let's say we put all these functions into a set, and let's call this set U. This means we have infinitely many functions in this set U. So we start with sine of x, then we go to sine of 2x, then sine of 3x, sine of 4x, and so on. And here please don't forget, these are all functions in the function space, so maybe we should write it like before. Moreover, we also see that no matter which number we choose in the sine function here, we always have a function that is 0 at the origin. Therefore, it makes immediately sense to include the constant function with constant 1 as well. And now being on it, we can also include all the cosine functions because the cosine functions start with the value 1 at the origin. In that sense, this constant function here belongs to the cosine functions and not to the sine functions. In addition, we should also extend this line now, so we have the cosine of 2x, the cosine of 3x, and so on. And there we have it. This is our whole infinite set U. It consists of infinitely many odd functions given by the sine functions and infinitely many even functions given by the cosine functions and the constant. So this is something you can already remember, but the important fact here from linear algebra is that this set U is a linearly independent set. In fact, this is not hard to show at all, but it has an immediate important implication. Namely, if you have a linear combination with these functions, then the coefficients are uniquely given. Indeed, this will give us a uniqueness property for the approximation later. However, first let's define such a linear combination. This means it's also a function from our function space, but now it lies in the span of U. Here please recall, span is just the common notation one has for the set of all possible linear combinations. However, in this special case, the linear combination gets a very nice name. Namely, we say it's a real trigonometric polynomial. And we add real only to emphasize that we are working in the real vector space. And with that said, I think you already know how such a trigonometric polynomial looks like. First, we scale the constant function and let's call the scalar a0. Then we can scale a finite selection of the cosine functions and add them, meaning we have scalars ak, where k goes from 1 to n. And n is a finite natural number. And now we have the different cosine functions here, so we have k times x inside. So very nice, and now we can also scale and add the sine functions. And in order to not confuse the coefficients, here we call them b1, b2 and so on. Otherwise it's exactly the same, these are real coefficients, and inside the sine function we have k times x. Hence this is something we should note here, ai and bi are in R for all I. So this is a trigonometric polynomial, and this is exactly what we will use to approximate a 2 pi periodic function. There you might recall from real analysis that we have Taylor's theorem, which explains the approximation with ordinary polynomials. Hence, this is something similar but also completely different because we don't have monomials here for the approximation, but the cosine and sine functions. And soon we will see that the approximation properties we have are also completely different. But before we do that, I also want to show you that we have a complex trigonometric polynomial as well. This means that now we have to consider the complex vector space of the 2π periodic functions. And then obviously not a lot changes, we can just say that we have a complex trigonometric polynomial as well. The only thing we have to do is to allow for complex scalars here in this equation. However, this changes a lot because in the complex numbers we have Euler's identity. And you know this nice theorem because it connects the cosine and sine function with the exponential function. And therefore, writing a complex trigonometric polynomial is much simpler. We can use the same amount of constants, but now we go from -n to +n. And then the constant is just called ck. And now instead of writing separately cosine and sine, we can put it together and write x of I times k times x. Of course, we can talk a little bit more how this connection actually works, but for the moment it's sufficient to know that we have two different notions of trigonometric polynomials. And also, it's good to know that the complex one has an advantage of being very compact. Okay, I think it's good enough for today. Let's meet in the next video when we put more geometry to these functions. In particular, we will talk about orthogonality. So have a nice day and bye bye.